Okay, next we are going to talk about energy. So this is chapter 7. And there are several types of energy that we can we need to consider in every problem. And so there's kinetic energy, potential energy, and internal energy. I'm going to talk about what they are. And there are also ways that we can change that stored energy. So maybe we can add or take away in the form of heat or work. Okay, so when we use the equation, it's really important, and it's very different than Wiley. Please get used to this. Start with this equation. Okay, again, in the equation sheet there's more specific equation, delta K split, delta U split, all of those are split. But this is the general equation because later on we are going to add more terms on each. So let's understand what these are first. So what is kinetic energy? So it's a form of energy that we can store in a body. The kinetic energy is equation is 1/2 mv squared. So assuming the object has a mass, right, and then has a speed as well, then it will possess kinetic energy. Okay, so it's the speed is the key thing here. Okay, because we know that we only deal with the objects which has mass, so we know that it's going to have a mass, and if it also has a speed, then it has kinetic energy, and we represent that with capital K. Potential energy is represented with U, capital U, and it is related to the elevation. So it has the mass of the object, gravitational acceleration, mg is related to the weight force, right? And also it depends on the elevation, so there is also and we use the elevation as y. So this is going to be very important because this y is always measured from the ground vertically upward, always. Okay, we have to make sure that we choose that. Maybe in our free body diagram it was a tilted surface and we made the x and y tilted, but for potential energy, when you apply energy conservation, you're going to go back to this case and you're going to say y is upward like this, and positive direction is upward. It starts from ground. Ground means y is 0 at the ground. Okay, so potential energy depends on the elevation. So when you're looking at the problems, if the object has a speed, then you have kinetic energy. If the object is changing its elevation, then you have potential energy change as well. Okay, for the internal, it depends on, I'm not going to write an equation, but it is represented with I, and it depends on the molecular level. So if there is any change in temperature or pressure, then we will have change in internal energy. Okay, most of the time so far we are going to ignore it and we're just going to say there's no temperature or pressure change, so the change in internal energy will be 0 then. But later on we will talk more about it, and we will even assign a part of it as due to the friction force. Okay, we will get to that later. And so these are the type of energies. Again, we will really look into more details. There are several forms of potential energy, also kinetic and internal. So we're gonna investigate those in more carefully this chapter and next chapter. But let's also talk about kind of what goes on the right side of the energy conservation, which is heat and work. So heat is, again, we are gonna use the symbol Q first of all, and there's no equation for this either. If there is heat added or subtracted from the system, then Q stays there, and then we are gonna find out what's going on. Is it positive value or is negative value? So we are gonna think about the right side. Most of the time that this is gonna be 0, and we're just gonna say no heat added or subtracted. Okay, and the work is something that we do investigate carefully. So you kind of go through all those energy forms and the heat. Think about if you have any 0 terms when you're applying this energy conservation equation. You leave work out, then you think about what to do with the work. Okay, so for the work term, we use the equation F dot D. So this is a dot product between F and D. One form of writing this, if you know the magnitudes and the angle between them, I usually use FD cosine theta. Okay, another form to write this is Fx dx plus Fy dy plus Fz dz. I use this form if the F and D are given in unit vector forms. So I'm gonna explain this in the next video of like doing the dot product, but this should give you some idea. And when we work on the work term for the energy, we need to draw free body diagram, okay, and see how many forces you have and how many work terms you will get, and then think about for each of them if whether they are 0, positive or negative. So kind of get their definitions and see what you're going to plug into the work term. But one thing so far, and I really want this to be clear, is most of the problems you will have the work done by the weight force, because the object has a weight, and if there's an elevation change, then that means the weight force is doing work. Okay, so there's elevation change, that directly means that the weight force is doing work. The thing is, when you apply conservation of energy and you are using this equation, you have 2 choices. Okay, and this is very important. This is different than Wiley, and you really need to understand this. Hopefully this is going to help when I say here in this video, and I try to explain it in the example problems as well. So you have 2, let me just get rid of these, 2 options, and in terms of the weight force is going to affect, or the change in elevation will affect these 2 terms. Okay, and if there's an elevation change, then that means there's a change in potential energy. Okay, so you either keep this, then say work done by the weight force in this work term will be taken to 0. Okay, although it is not 0, I'm not gonna put that work done by the weight force in the work term, because I'm counting it in the potential form. Okay, or you can do the opposite. You can keep the work done by the weight force on the right side in the work term and get rid of delta U, and then say this is counted as work done by the weight force on the right side. Okay, and the relation between them, the definition or the relation between them is delta U is negative work done by the weight force. Okay, why is it negative? Because again, if you look at the equation, they are on different sides of the equation, right? If you put that WW on the left side, it becomes negative, but then you don't put delta U, so you're really replacing delta U with the negative of WW, right? So that's kind of reason that we have that negative, because they're on the 2 opposite sides. But important thing is choose one of those, okay? Don't do both of them. You have to be careful with that, because if you keep your delta U and the work done by the weight force for the work term, then you are double counting it, and that will result in a wrong answer. That is very important. There's more coming up like that. There will be other stuff. We will be able to do this, and we need to understand what it affects in the conservation of energy equation, and then what is our choices, and then we need to do the right thing and not double counted.